Hey, hi everyone, this is Avinash here, and my topic for the short story presentation is multi speaker text to speech synthesizers approach based on transfer learning. Let's hop into the topic. Before going on the details of the paper, let's understand a few key terms. What is text to speech? What is a multi speaker DTS system? What is transfer learning to better understand the topic? What is a text to speech system? Any system that has the capability to convert a normal language text on any computer or digital form into an audible speech output is called as a text to speech system. So, as the name implies, it's basically converting a text to speech. Uh, what is a multi speaker TTS system? So, a multi speaker TTS system synthesizes speech with different voices with a single model. So, for different voices, you don't have to retrain the model again and again. So, you can use a single model for synthesizing a speech or any audio or video with different voices. Then, what is transfer learning? Transfer learning is one of the key aspects which paved way for a lot of development in the recent trends in AI. It is basically a research problem in AI ML space that focuses on storing the knowledge that we have gained from solving one problem which can be reapplied in a different but a relatable problem. So consider a case where you have used or trained a model for classifying cats and dog, and if you want to perform classification of lions and tigers, what you can do is you can get the get the cats and dogs model, freeze few layers, add more convolution layers, and a deep neural network at the end, and followed by a software can perform a classification on top of it. The results would be pretty much great rather than training the model from the beginning. It reduces a lot of time time and it makes the process even more efficient, and the model and even the neural network converges in a better direction. So now let's go to the typical model architecture of a text to speech system. There are typically three important components in any text to speech system: a speaker encoder, a synthesizer, and a vocoder. From this diagram, you can see that the speaker speech signals are passed onto the speech encoder, where it return back and fixed size embedding vector. So what the synthesizer does is it takes the fixed size embedding vector from the speech encoder along with the text, and it produces the MEL spectrogram. The MEL spectrogram is passed to the vocoder, which returns a time-based waveform as an inference. This is basically the high-level overview of a text-to-speech system. As I told in the previous slide, the three components are the speaker encoder, the synthesizer, and the vocoder. The speaker encoder generates the fixed dimensional embedding vector from a few seconds of reference speech from the target speaker. The synthesizer predicts a MEL spectrogram from the input text and an embedding vector. The vocoder infers the time domain waveform from synthesizer's MEL spectrogram. So, for comparing the author's design with an existing system, for the existing baseline system, we are considering the current the quarantine German real-time voice cloning system. It's currently the most widely used system for trying out any voice cloning activity in the open source space. It is designed on top of a Google research paper. So coming to the architecture of this paper of the baseline system, it's basically a speak encoder with three LSTM layers and a final layer. Each has 265 units, And coming to the synthesizer and the vocoder, the synthesizer is a sequence to sequence model with an attention layer on top of it, and the vocoder is a wave RNN. So this is basically the architecture design of the Quarantine Germain real-time voice cloning system. And coming to the proposed system of the author for the speaker encoder, there were the author tried out various neural network architecture for the speaker encoder system and have tabulated the results of how each of the system performed and what was the error rate. So coming to the various speaker encoder architecture, he tried out with 5 convolutional 1D layers, one GRU layer and a final linear layer, and 3 convolution 1D layers followed by 2 GRU layers and followed by linear projection layer, and 3 GRU layers each followed by a linear projection layer, and one convolution layer for and 3 GRU layers and each followed by a linear projection layer, and one convolution 1D layer and 3 LSTM layers each followed by a linear projection layer. So these were the different architecture that user tried out for the speaker encoder component. And let's get to the error rate tabulation table. Here for each of the neural network architecture, the author tabulated them, the step size and the training loss, and how the equal error rates work for various neural network architecture. And as you can see, the advanced GRU has a very less speaker verification equal error rate, so it's performing good. Now coming to the similarity evaluation factor, as you can see, while clustering the ground truth with the corresponding generator speaker labels, the model performs and synthesizes pretty well, as it was able to identify the speaker label with ease. It performed very well. Now coming to the subjective evaluation, the MSSS of the base in the proposed system, the mean square error of the base in the proposed system is, as you can see, the baseline is around 2.59 plus or minus 1.03, and the proposed system is 3.17 plus or minus 0.73. So what the authors are trying to conclude is the research authors' main goal was to create a voice cloning system that could generate natural voice for a variety of target speakers. That's basically for a multi-speaker multi-speaker synthesization while using just minimal data. Their system combines a speech encoder network that has been trained independently and a sequence to sequence with attention architecture for synthesization and a neural vocoders model. The synthesizer and a vocoder can generate good quality speech even for speaker who has never been observed before by using a transfer learning technique. Despite this experiment demonstration provides a reasonable similarity to the real speech and improvement over the baseline system, the proposed system fails short of human level naturalness when we are comparing it to single speaker results. The author results perform well for multi-speaker systems, but for a single speaker system, it falls literally short compared to the natural level, human level naturalness. For further understanding about this topic, you can go to the paper published by them to understand in detail about the how the speaker encoder architecture works. So as you can see from this architecture diagram, inside speaker encoder, they have an GRU layer followed by a TANH layer, TANH as the hidden layers, GRU with TANH as the hidden as the neural network architecture, followed by linear layer with a ReLU activation layer, and convolutional neural network with max pooling and ReLU. So this is how the speaker encoder architecture works. The input frame goes to the convolution layer and goes to the GRU layer, which all are stacked, and it provides a embedding vector which is theoretically stated as a D vector. as I already saw, the synthesizer and the vocoder. The synthesizer gets the text and the embedding vector from the speaker encoder and generates the ML will from the well form goes to the vocoder, which provides the timed waveform. And to better understand the transfer modality, you can Google about the transfer learning and how it works, and how the multi-speaker transfer learning approach works, and how it would help in solving a lot of problems by reducing that time. I just showed you guys the experiment results here. If you want to see the detailed experimental results, you can come to the paper and understand the detailed experimental results and the reference topics that are used by the authors for formulating this paper. Also, I have written a Medium article for this topic based on this research paper. Kindly have a look into it if you have any time. Thank you, guys. Have a great day. Bye bye.